Hello, my name is Theo, and this is design and testing of a magnetohydrodynamic oxygen generation cell for microgravity operation. So some background. What you see here is a notional, but qualitatively correct mass versus mission duration plot. You'll notice that there is an essentially exponential curve for the stored consumables and a linear curve for a regenerative life support system. And some missions that we all know fall in these places. And what you'll notice is that there's a break-even point somewhere where it is more mass efficient to launch a regenerative system than simply bringing bottles of oxygen. For the mission duration of the ISS, the Oxygen Generation Assembly, OGA, has been well suited to the mission duration. That assembly went online in 2007, and in the last 18 years has produced many times its own mass in oxygen. For the Mars mission duration, which is on the order of 3 years, that design of the system would not be enough to overcome the mass penalty of launching all the hardware required to close the loop on the regenerative system. And so it's clear, and this is based on a systems analysis that was done, as you see at the bottom. And so it's clear that we need a new architecture if we want a regenerative system to be more mass efficient than stored consumables for that particular mission duration. What this new architecture would do is essentially lower the slope on the mass curve by increasing reliability and thereby reducing the number of spares so that the launch mass is reduced and the maintaining mass is lower for that different system. And if we can reduce astronaut required time for maintenance, and increase robustness and reliability in other ways, that would also be ideal. So the proposed architecture is the Magnetohydrodynamic Oxygen Generation Assembly, or the MOGA. And what you see here is an alkaline electrolyte, potassium hydroxide, with anode and cathode separated by a membrane, which keeps the evolving gases of oxygen and hydrogen, respectively, on separate sides. There's a magnet around the outside. And what this does is the current density field crossed with the magnetic flux density field produces a Lorentz force on the bulk electrolyte. And what that does is it swirls the flow such that the liquid, which is more dense than the gas, is forced to the outside, and the gas can be extracted from the inside. This design is geared specifically for microgravity operation because it's very challenging to accomplish reliable phase separation in the microgravity environment. And if we can combine both gas generation and gas evacuation in the same cell, we could dramatically simplify the architecture and save launch mass. It would reside within a larger oxygen generation assembly, which would rely on heritage orbital replacement units, ORUs, which have been used on the International Space Station for the last couple decades. So here's what that looks like. The video that you're about to see is observed from above, and we have ring annular electrodes with a magnet around the outside. And what you'll see is a swirling field. This is a microgravity test in a drop tower, an experiment run by Dr. Alvaro Romero Calvo and Dr. Katharina Brinkert at Bremen. And you'll notice that the flow, which is resulting with from no moving parts, accelerates the bubbles toward the center, and the liquid electrolyte is forced toward the outside. So the point of no moving parts is that those tend to malfunction in space. Gears don't do well with long-term storage or the loads from launch. And so by eliminating the recirculation loop shown here, which includes a pump here and a rotary separator accumulator, which is what currently accomplishes the hydrogen gas and water separation. If we can eliminate this recirculation loop by performing phase separation inside the cell stack, then we would dramatically simplify the architecture and reduce the number of spares launched, reduce the launch mass. There would be an added potassium hydroxide refill, which would be a nominal on the order of 20 kilograms for a 3-year mission. And there would be a group of drives for the analysis that was done. There were an assumed 2 drives such that one could maintain oxygen generation while parts were replaced on the other. But what you'll notice that's missing is the recirculation loop along with the rotary separator, because phase separation is accomplished in the drive and pH balance is no longer required, because the membranes used for PEM, proton exchange membrane electrolysis, on the OGA and alkaline electrolysis are very different. The alkaline one is much more robust. So here's the prototype that we built to test some of the models used in the optimizer for this system. The dimensions were drawn from the optimizer for building a representatively sized electrochemical cell for the spaceflight application. This is 10 centimeters or 10 inches or 25 centimeters in diameter. And here is what the inside looks like. You'll notice there's a plastic casing, stainless steel electrodes, the Zirfon membrane, which allows ion transport through, but restricts gases to their respective sides. There's a ring of magnets around the outside, and those are coated in an insulated coating just in case leaks occur. Here's the cross section. For the horizontal testing, you'll see in a moment, the upper acrylic and the membrane were removed, and the fill and drain ports here were designed to allow for operation in the vertical orientation so that refill electrolyte can come in the bottom and gases can escape out the top. We're testing in Earth gravity, whereas the design is optimized for microgravity. So we had to kind of split the difference there. Here's what the experimental setup looks like. You'll notice the membrane is removed, the top acrylic is removed. We're looking down from the camera here into the drive, and then we're imaging the flow. And what you'll notice, current densities of 50 and 300 milliamps per centimeter squared. And you'll notice that a similar flow is what you saw in the drop test is produced. And you can see that the angular velocity is qualitatively scales with the current density, which is what we expect from the Lorentz force. And you can also see that there's some turbulent regime here as the layers of bubbles and the flow on the outside shears against the flow on the inside. Here's a current density series. You'll notice that the bubble froth comes more toward the center in the lower current densities, whereas there's a central area in the upper current densities where this bubble froth is evacuated to the atmosphere before it can get to the center. The analysis that was done was using this tracker float, developing a rotation time series, as you can see on the right here. And from that, we can extract angular velocities, which are the slopes of these curves in the angular displacement and time axes here. You'll notice that as we expect, increasing slope occurs with current density. You'll notice that the upper current densities are linear, much more linear, which indicates that the rotation was much the rotation rate was much more constant. The tracker also stayed much more at the same radial position in the drive during testing, whereas the lower current densities, the float gravitated toward the center, as you can see with this upswing, and that's likely due to flow asymmetries as a result of bubbles getting caught on the upper electrode. Again, we're in 1G as opposed to microgravity here. So those are some of the differences among current densities. And here's how that compares to the model, which is a torque balance between the magnetohydrodynamic torque from the Lorentz force and the viscous torque drag on the walls in the drive. You'll notice that the model predicts within 18% of the current densities that we're interested in. It underpredicts at low current densities, likely as a result of current density asymmetries. Again, bubbles on the electrodes, most likely. The model does not capture turbulence at the upper end, so we're over predicting as we go to the higher current densities. The electrochemical model is a very different story, however, because of the lack of optimization of orientation relative to gravity. Again, bubbles are sticking to that upper electrode, which is dramatically impairing performance. And there was no optimization of the electrodes for electrochemical parameters. They were stainless steel and simply sandblasted to create an even surface. And so in the flight model, there would be a lot more optimization done. The model is linear as opposed to logarithmic, as TOEFL slopes would predict, just based on uncertainties around what activation over potentials we could expect for this future technology for nickel electrodes in an alkaline environment. Um, so a significant development would need to be done to validate and that would only really be possible in a microgravity environment. So that was kind of out of the scope of this project. Overall, what this means is that the magnetohydrodynamic model is what we expect, which is a great check. And we are working on the phase 2 for the NASA NIAC proposal, supported by our collaborators at Giener Labs and those at ZARM in Bremen, Germany. The parameters for the optimized drive are shown here. There would be 24 cells required to support 4 astronauts at 25% margin. And the power and waste heat are shown there. The optimized parameters for the drive are shown here relative to the prototype that was made. So the in the flight model in the flight design based on these models, we would shrink the outer diameter, shrink the magnet thickness, increase the electrode gap to allow for more rapid gas evacuation between the electrodes. The cell voltage, as discussed before, would be very different based on the performance in the microgravity environment. And we were right around the current density that would be optimal for this operation. The end result is that accounting for the other modules, the orbital replacement units that would be required for the MOGA, the mass savings are shown here relative to the currently operating OGA on the ISS and the future oxygen generation assembly, which is accounting for advancements in the advanced OGA, which is in development now, scaled for the oxygen generation rate for the MOGA, just so we're comparing apples to apples. The crew time in both cases would be reduced by about a fifth, which is significant for saving valuable astronaut time on a trip to Mars and back again. Other advantages of this architecture include resistance to feed water contamination. The proton exchange membrane electrolysis membrane is much more sensitive to impurities, whereas the alkaline architecture is much more robust to those. Resilience to dormancy. There would be approximately a year and a half by some mission CONOPS of dormancy in Mars orbit as the astronauts descend to the surface. And the alkaline architecture is much more resilient to that dormancy period. And then component level swappability is something that has been discussed for the AOGA, and it's something that we've incorporated here to understand what the benefits are for example, allowing single cell replacement or complete drive replacement while maintaining the magnets where they are, that kind of thing. So the bottom line is that the MOGA is a promising alternative for exploration crewed missions to Mars or beyond. So thanks for your attention today, and we're excited to continue developing this as a part of the NASA NIAC Phase 2, which will be beginning later this year. So thanks very much.